Hello, and welcome to Orion's Hunt. In this game, you have a bow and a quiver with 11 arrows. In the game itself, there are 3 targets, 2 stationary and 1 that rotates. Your goal is to shoot all the targets before the rotating target stops spinning.
For every 5 points you score, you receive 1 star. This star goes on our game.
Here is the physics behind our game. When we first set out to create a carnival game, we immediately knew that we wanted a game with a spinning target. Our inspiration to get the target to, spin was a mousetrap. That sounds odd, but just listen for a second. A common first project in any STEM elective is the mousetrap car, which the young engineers are told to create a car that travels a certain distance while only having a mousetrap as an engine. This type of mechanism would allow for a wheel to spin for a long time after all the energy has been released while still being extremely simple. Therefore, we use the same mechanism for our targets. The target would be powered by a mousetrap car-like mechanism with an arm and spring to crank back and gain potential energy before being let go and rotating a dowel rod connected to the target. We were originally going to use paper clips due to the tension of being able to work as a spring, but unfortunately, we were not allowed to use them. So we tried using multiple different alternatives as a substitute for paper clips, including paper, cardstock, cardboard, string, and rubber bands. Eventually though, after a week, we figured out how to get this thing to work. The way our mousetrap works is as follows. We have a thick dowel rod with a rubber band on it, and that's attached to an anchor at the base of our project. When the dowel rotates, the rubber band stretches around the main dowel, causing tension to build up. Before we release the tension, the dowel rod is in a state of balanced forces, meaning that the dowel rod is not accelerating. No, it's completely still. Meanwhile, we also spool strings around another, thinner dowel. The string is tied on the end of another dowel, which after we finish spooling the string, we insert into the main dowel rod. After a bit more spooling, we let go, and the rubber bands pull the main dowel backwards, causing the string to unspool and the small dowel to rotate. Attached to this dowel is the rotating target. This would be an example of an unbalanced force because the dowel and target accelerate from stop position to rotation. After all the string is gone, there is still lots of momentum thanks to Newton's first law, also known as inertia. The mass and diameter of the target keep the target spinning even when it's not actively being powered. On Thursday, March 7th, 2024 at 10:24 p.m., Sham had a Rocket Boys moment. And then we knew it was time to nerd out. By the way, I didn't put that in the script. It's I don't know who put that in the script. I'll just probably add it in the edit. But seriously, guys, why did you put that in the script? We were able to calculate the amount of potential elastic energy in the rubber bands that power the mechanism by finding 1/2 of the spring constant, or the stiffness of the spring, 5 newtons per meter, measured in newtons multiplied by the distance squared. The distance can be found by multiplying the circumference of the large dowel, 8.792 centimeters, and the number of rotations that the rubber band can make around the large dowel, 6, which gets a distance of 52.752 centimeters or 0.53 meters. Squaring the distance, then multiplying it by 2.5 and dividing it by 2 gives you around 0.7 kilograms meters squared per second squared, or 0.7 joules. From here, we found force by simply dividing the energy by the distance or the circumference of the main dowel times the number of rotations. 0.7 joules divided by 0.53 meters is equal to around 1.22 newtons. The cool thing is, this is the exact amount of force we put into spinning the dowel rod. The law of conservation of energy says that no energy can be created nor destroyed, so the energy we put into the dowel is released in the same amount of force that the target spins in a perfect, frictionless world. However, some of that energy is converted into heat and friction. Nonetheless, accounting for the heat created, the total amount of energy is the same. Thanks to this law, we can also find the speed using the kinetic energy formula, Ke equals 1/2 mass times velocity squared, we can plug in our energy value, 0.7 joules, for our kinetic energy, plug in the mass of the target, 0.16 kilograms, and solve for velocity, giving us a value of around 1.48 meters per second, or around 3.31 miles per hour.
After figuring out the speed, which is a scalar, a measurement with no direction, and the velocity, which is a measurement with a direction or a vector, we were also able to find the acceleration of the target by plugging in
The force
into the Newton's second law. Force equals mass times acceleration.
We simply took our force of 1.22 newtons and divided it by the mass of the target, which is 0.16 kilograms. After dividing out, we end up with 7.625 meters per second squared, or 17.06 miles per hour per second. In other words, it speeds up by 17.06 miles per hour every second in a frictionless environment. Another major part of our game is the bow. After realizing we need to somehow get people to hit the targets and make it stick, we decided to go with Orion's main weapon, the bow. We decided to make a compound bow as it would be more sturdy and consistent. The three main parts are connected by two joints which are held in tension by two folded rubber bands. These rubber bands, when stretched, will store up energy and release it into a cardboard box, killing force. This is an example of Newton's third law of motion. For every action, there is an equal and opposite reaction, where the action is the bow pulling back and the reaction is the tension of the rubber bands pushing on the arrow.